Okay, so the afternoon session is going to start, and the first lecture will be given by Dr. Andra Nemcová. She is from my home university and the same faculty of engineering and communication. But the other department of biomedical engineering, which is quite close, some topics, related topics. So, Andra, the floor is yours.
Thank you.
Be welcome.
Thank you very much to be here. It's a pleasure for me. So, good afternoon. My presentation, the topic is the use of PPG from smartphone or wearables for health assessment. So that's the area which I'm focused on. And we can start. So I think all of us have a very powerful tool in our hands or pockets or on our table, and it is smartphone. And it can be used for many things, but it can be used also for health assessment, for estimation of many health features. So that's something we will talk about it today. So the smartphone has more than 70% world population. So it's quite a lot of devices, and that's the power which is in this device and this area, I think so. It is low cost because we already have the smartphone. All the measurements we would like to do can be done on the spot, so we do not need any other sensors, and we can measure ourselves whenever we want to. It is non-invasive, it's quite clear. We can measure ourselves 24/7, so it's a good thing as well. And it can be used also in telemedicine, which is quite developing area and very useful. The smartphones and the health assessment using smartphones can be done maybe probably in prevention area, which is quite interesting and useful, because if we have some medical devices which are intended for some diagnosing and monitoring of people which are diagnosed with this disease, so then we use already the specialized devices. But for prevention purposes, smartphone is a good tool. And it can measure the PPG, which is the signal. We will talk about it today. And it can be also connected with wearables. It's even more powerful tool. It is connected because the wearables are more specialized. They have better sensors in some way. So the connection is very good. On the other hand, there exist minimum applications which are certified as a medical device, but there are some of them, and we will end this presentation with these applications. So it's quite interesting area that there are some of these. We will start with a brief introduction with what is photoplethysmography, the PPG. Maybe question for you. Do you know what is PPG? Who knows? Raise your hand, please. Okay, so that's fine. We start with some introduction, what it is, because it's quite important to understand it for the rest of the presentation. So PPG, photoplethysmogram, is the signal which is measured using some, let's say, optical device. It can be the smartphone, it can be smartwatch or pulse oximeter. Maybe that's the one you know the best for blood oxygen saturation measurement and heart rate.
Sorry that I interrupt, but we are not able to see screen. Did you hear me?
Yes, we can hear you.
We don't see the presentation.
Okay. I think we will fix it. It takes a few minutes maybe. So I think we can continue and you will see it later maybe. So the heart beats, we know, all of us knows this, and it products the pulse wave, which goes through our arteries to the periphery of the body.
Just a second. It seems that it is not seen. I don't know why. We'll try it once again.
So in this time, we can maybe try one experiment if you want to. It's something like this. You can take your smartphone. You can open your app for video recording, switch on the light, the LED light, the flash, and you can put your finger on the camera. And if it is correct measurement, you should see something like this, orange or red screen. And if you have good eyes and warm fingers, then you will see some pulsations.
Yeah, that's okay. So sorry.
So you can try this to believe me that there is some signal which can be processed from the video signal. So the heart is beating and the pulse wave is going through the arteries, and we can detect the pulse wave on our fingers, wrist, or ear. It depends. But here we have the finger, so we can talk about this scenario. And we can do it optically. We need two things, and it is the source of light. Usually the LED lights are used, and some photo detector. It can be in any device, smartwatch, or it can be in smartphone, as you can see maybe now. So that's why it is called photon, because we have some light. Platismo, it means changes of volume, and it is here because when the pulse wave goes through the arteries change the volume. And graphy means we have some signal from it, or so that's photoplatismography. And from this video, I will show you on the next slide how is it processed to obtain this signal, which you can see that there are some pulsations. It means each pulsation is one beat of our heart. So if we have, for example, smartwatch, it works on the same way. We have these two light source and the detector on the same side. In case of pulse oximeter, it can be on the opposite side, and the light goes through. So here is some schematic view how it works. Here we have the light source. It goes through various tissues, other tissues, venous blood, non-pulsatile component of artery blood, and the most important part, which is the pulsatile component of artery blood. And if we detect the light which goes through or is reflected, then we get this signal, which is the photoplatismography. It has also the DC component, which is changing very slowly, let's say, and AC component, which is the pulsatile one, and it corresponds to the beats. And maybe you noticed, if you have some smartwatch, you notice that there is some light which is blinking time to time, and the light has usually green or red color. And it is connected with the depth of light penetration. So green light is somewhere in the middle, and the red light penetrates deeper in the tissue. So it may be better or the combination is usually used. In case of professional pulse oximeters, we have two different wavelengths in the red and infrared areas. So that's why green and red light. And also there can be various sensor designs which is connected with the quality of the signal. And regarding the sensor design, it is important what LED light we have, what is the wavelength of this light, and what is the intensity of this light. So here we can see it in this picture. Then the sampling rate and also the positions and number of LED lights and sensors is also very important. If you turn the smartwatch, maybe you will see more LED lights and more detectors. So it's for the better quality or to improve the quality. And also the sensitivity of detectors and some other features of detectors. The signal has the useful component in the frequency range of 0.1 to 10 Hertz. And the heart rate is somewhere around 1 Hertz, means 60 beats per minute, which is, let's say, normal heart rate. But there are also some briefing components, etc. So it is useful as well, or maybe. So here is a slide for what is behind, how to create this from this. And there is some explanation. We have the video, which we record with our smartphone, and we decompose it into the three color channels, red, green, and blue. And then in each color channel, we average each frame of the video. And from this, we have only one number, which is 1 point in this signal. So maybe now it is more clear how we can get 1D signal from video. And then we have three PPG signals from the smartphone. In case of different devices, we can have only one. It depends on the detector. So it was PPG. We will talk about smartphone later. And now we have a slide regarding wearables. What can be imagined when we say wearables with PPG sensors? So we can imagine a smartwatch. Maybe some of us have the smartwatch. We can imagine some, this is some scientific bracelet, let's say, from which we can get also the raw data, which is quite useful. And some bracelets, which are simpler than the smartwatch. And also smart rings, smart earrings, and this is center for sportsmen or athletes, which can produce also raw data. So it's very important for us as scientists because we want to work with the raw data. Maybe you know any other device which can produce the PPG signal, or it can show you the heart rate, and it is done optically. Maybe not. Yeah, and what about the PPG signal? How it looks like? It is quite simple signal. Let's say it has only two main peaks, sometimes only one peak. The first one is systolic peak, and the second one is diastolic peak, and between them is something which is called dichrotic notch. And when the person is older, or in some cases, there can be only one peak. There is no dichrotic notch, and it's physiological. The dichrotic notch disappears when the person is older. Yeah, and we can divide it to anachrotic phase, which is the rising, and the catachrotic phase, which is part of the signal. It is connected also with other signals. Probably you know ECG signal, electrocardiogram, the main signal I think, which is recorded from heart or from the the electrodes are on the skin, but it gets the information about heart and function. And here is another signal which is connected with heart, and it is phonocardiogram, which is measured by microphone, and it is mechanical activity, let's say, of the heart. And there is some connection which is used then for estimation of various features, for example, the blood pressure from the PPG and phonocardiogram or the ECG. And here are the features. It is pulse arrival time, which is time between R wave in ECG and the peak in PPG. Because the PPG, as you can see, is delayed because it's the pulse wave. The ECG signal and the phonocardiogram are measured very close to the heart. On the other hand, PPG signal is measured on the periphery usually, so there is some delay, which can be used for example, blood pressure assessment or stiffness of artery. And the second thing, which is for us important, is vascular transit time, which is the time between the first heart sound and the PPG peak. And we will see this feature later when we will talk about estimation of blood pressure. There are many features which can be derived from the PPG, so it is quite useful because nowadays many methods are based on machine learning, so it is necessary to extract some features, not only these ones, but these ones can be extracted directly from the PPG. We can have then, for example, the first, second derivative, can have spectrum of signal, etc. So there are many more features which can be used. And let's go to the smartphone sensors. It's just maybe brief information because I think it's quite interesting. And I don't know whether you know that your smartphone has so many sensors, maybe yes. So all of these sensors can be built in your smartphones. Some of them are not. It depends on the quality and price of your smartphone, maybe. All of us know that the smartphone has microphone and camera, probably. And there are some other interesting sensors, such as proximity sensor, light sensor, which are here. Then sensors for motion or position analysis, which can, for example, count our steps. It's, for example, accelerometer, magnetometer, gyroscope, GPS. Barometer can calculate the height or number of stairs we have through the day. Then we have also, for example, humidity sensor, thermometer, which are environmental sensors that measure something around the phone. But today we will focus on camera because we want to measure the photoplethysmogram, which can be measured only this way. On the other hand, the heart rate, for example, from using the smartphone can be estimated using also accelerometer and microphone, for example. If you want to do some experiments with your smartphone and want to know what sensors are in your smartphone, you can download this application, which is called phyphox. It looks like this, and here you have access to the sensors of your smartphone. Maybe not all of them, but majority of them. And there are also some experiments which can be done with these sensors, so it's quite interesting. And it is for both main platforms, for Android and iOS as well, so it's good. Here is table where are the differences or advantages and disadvantages of smartphone on the left side and wearables on the right side. So the smartphone is always with us, or usually with us, and we do not need extra costs to buy something to make the health assessment functional. Sometimes it is necessary to pay some smartphone application, but it depends. On the other hand, the smartwatch has smaller number of users. Not all of us has some wearables or smartwatch, something else. And it can be expensive for quite many people. It can be expensive, and it also the quality of health assessment also depends on the quality of smartwatch. So it's connected. The smartphone is suitable for short-term measurements because we do not have it attached on some part of body. And that's why it is quite advantageous in case of wearables that they are intended for long-term monitoring. So we can measure, for example, through the whole day. It's not possible or comfortable using the smartphone. So if we want to monitor ourselves using the smartphone, it's necessary to be active to make the measurement. And in case of wearables, the measurement is passive because the smartwatch measures our heart rate, for example, during the whole day, and we do not have to do anything. The smartphone has a camera and flashlight. On the other hand, wearables have sensors which are specialized on measurement of PPG, and also the LED light is usually has some proper wavelength. Flashlight is white light, which means there are more wavelengths, so it can be a disadvantage in case of smartphone. And also the number of sensors and lights are better in the smartwatch because here we have only one camera and one LED light. But the combination is quite useful, and each device can be used as well, I think, with a good result. We go to the signal quality because it is very important in case of PPG. It is very important in case of all signals, but especially in case of PPG, because if the pulse wave goes through the tissue, the changes between the peak of the pulse wave and the valley of the pulse wave is only 2%. So it's very small change, and it means that any motion can disrupt our measurement, and we will have noisy signals. So it is quite important to notice this and to also assess the quality of the noise of the signal. The types of noise can be different. It is usually the motion noise because we move our finger, we move the sensor, we go, laugh, walk, we can do anything, and it causes changes. It can be also, the noise can be also present in the signal because of the sensor is not properly attached to the part of the body. And also breathing can cause noise, but we can use it for example, respiratory rate estimation. So it can be useful noise. And also the light changes can make noise, and but it depends. There is the light source in the sensor or near the sensor, so it can do some changes, but usually the signal is not corrupted as the whole, but it can be used for some analysis. The denoising is difficult because because of this. It's quite difficult. Sometimes it is possible, but if the signal, the motion is bigger or higher than the signal, then we cannot do anything. And that's why we need to assess quality of the signal to prevent some false alarms, such as our heart rate is too high and it will be repeated 20 times a day, so it's not very good. and it causes alarm fatigue, so-called alarm fatigue, and then the device is for nothing because not pay attention to alarms. And we can also prevent incorrect results and maybe some misdiagnosing. So here we have some algorithms, let's say, how to assess the quality of the signal. It is usually done using AI. It is, I think, common for all the things we have here today. But there are some methods which are based on some rules, let's say, and features, and it can be better explained on these. So the classification can be binary to good and poor quality signals, and we will then use only good quality signals for further analysis. It can be classified to more classes if we want to, for example, just calculate the heart rate or do any further and more difficult analysis, such as blood pressure estimation. So we can start with physiological rules, where we assess the rhythm of the signal of the heartbeat. Here we have, for example, rule whether the heart rate is between some range, whether the interbeat intervals, the distance between two peaks, is within some threshold, etc. And we have also template matching, which comes also with morphology of the signal, which is important as well. And it is pictured here. Here we have good quality signal, and the peaks are detected. Then they are averaged, and correlation between each peak with this template is calculated. And then if it is above some threshold, it's good part of the signal, and vice versa. So this is good signal, and here we have poor quality signal, and here we can see that the beats are very different, and maybe the template doesn't make sense, and the correlation will be very low. So this is just one example how the quality can be assessed. The methods there are many methods for quality assessment, and it's quite important part of signal processing. And now we go to health assessment. So it means the features which can be assessed from the PPG signal. Maybe this is the most interesting part. And I will talk also about some data sets which were measured in our department, because sometimes if we want to analyze something or develop some algorithm, we do not have proper data. So we need to measure our own data, which is quite time consuming, but necessary. So what can be estimated using PPG? We talked about heart rate, so it's quite clear. We can assess somehow or evaluate heart rate variability, but we need, let's say, longer signals, at least 5 minutes to make sense. We can calculate respiratory rate, means how often we breathe per minute. Blood pressure, blood oxygen saturation. We can also estimate glycemia, which is quite interesting because it is non-invasive. And we can also detect cardiac arrhythmias. Just some of them we will see. So here are some pictures from our work at our department, and some of them are from some scientific journals. And I would like to start with peak detection because it's important for more types of analysis. So here we have some algorithm which was created by our colleague, and it works very well. It is based on UNET, and here we have some examples of results. It works even if there are some arrhythmias in the signal. So it is quite good and important for further arrhythmia detection. So that's the deep learning method. And for peak detection, then we can calculate just the difference between the peak's position, and we can calculate the heart rate. It is, let's say, the simple part of the process. We can detect heart rate also in spectrum, in frequency domain, and we can use some different methods. Here I have another example where we used wavelet transform to decompose the signal which was measured. And here are the frequency bands after decomposition. And we find the proper frequency band and calculate the heart rate, detect the peak, and calculate the heart rate. And we can also use some machine learning and deep learning methods, which is common thing. Just note to accuracy of this, the maximum error of this method for heart rate estimation was 0.8 beat per minute, so it's quite accurate method. Then here we have the database, which was measured by us, and it's intended for the quality estimation and also for heart rate estimation from PPG signals. It was measured by smartphone, different types of smartphone. And as a reference, we measured the ECG signal, which is important to annotate the database in terms of quality, in terms of heart rate, and it can be used also as a reference for peak detection, because here we have the positions of QRS complexity. We measured also blood pressure, glycemia, and blood oxygen saturation, so this is also the reference to these signals, and this database can be used further, for example, for blood pressure assessment or estimation from PPG. So here we can see two examples. First one is for good signal, and the second one is for poor signal. Now the database has almost 4,000 signals from 50 people, and we prepare extension because we have measured 110 new people and have more than 5,000 new signals. So now we need to annotate all of these signals, which is very time consuming. So we try to automatize this process and make the process more quick. And it is available on Physionet, which is quite a well-known repository of biosignals. So it's for free there. Then we have blood oxygen saturation assessment, which has or extract two features: the slope of the rising part of the PPG signal and also the height of the peaks. It uses two PPG signals, two color components, the red one and the green one. And then these two features are here in this equation. So it is the blood oxygen saturation calculated using this equation, where we have also absorption coefficients for deoxyhemoglobin and oxyhemoglobin. And there is some optimization of this method, which was done by us. And the mean absolute error was 1.1%. So it's quite good as well. Here we have respiratory rate estimation. Maybe some note at the beginning, because respiration modulates the PPG signal in three ways. It is baseline wonder. It is seen here. It's the slow wave, and the faster wave is on it. Then it is amplitude modulation, the difference between amplitudes in each beat, and frequency modulation. The beats are the distance between the beats are different, and it depends on the inspiration and expiration. So here we used very simple methods, just some low-pass filtration, and there are few variants of it, autocorrelation of this signal. then we try to extract this amplitude modulation. So we need to detect the peaks, and then here we have the points. So we did splice interpolation and have the respiratory signal. And then we calculated the peaks, or we extract the respiratory rate in frequency domain using Fourier transform. So the result was, or the error, mean absolute error was 1.5 or 1.3 for two different data sets, breaths per minute. So it's quite a good result. Here we have the blood pressure. It can be measured without the cuff. It's quite interesting. Maybe now it's common. I don't know. Do you know that blood pressure can be measured without cuff? Okay, thank you for your response. It can be measured. There are two different approaches to this. We can measure two signals, as we said before. It's the phonocardiogram and the PPG, and we calculate the difference between the first heart sound and the peak of the PPG. That's the vascular transit time, and that's the feature which is connected with blood pressure. Or we can use some machine learning and deep learning methods. We can extract some features from the PPG. It is possible to use only the PPG signal. And it's on the next slide, so we talk about it a little bit later. So here we need two sensors, and these signals need to be well synchronized, because it is very important to calculate this precisely. And it is measured like this. So we have the finger on the smartphone, and the smartphone needs to be near to the heart to listen the heart sound. But it is possible to measure on your own as well, if you have, or all of us have application for voice recording. So if you place the phone near to the heart, maybe you will see some regularity and the heartbeat. And we also need one feature which is called ejection time, and it is the difference between the two heart sounds which are visible in the cardiogram. And also weight, height, and age of the person. And then we can calculate the blood pressure using these equations. It is not important to go through all of these equations, but just to understand what is behind the blood pressure measurement. So this is one way, and this is the second way. It's with the use of AI. This is with the use of deep learning method. The UNET was used for this. And as an input, we use PPG, red and green PPG from smartphone, and also some information about the person, for weight, height, age, and gender. And we try to estimate the blood pressure continuously, which is not very common, because if you measure your blood pressure using the cuff methods, you obtain only one number and not the whole signal or the whole curve. So it was quite difficult to obtain the reference signals for this, and we had to measure our own using specialized device, because measuring blood pressure continuously, it is not very common, even maybe in hospital in some specialized places it can be done, but usually invasively. So here we use Peñas method and the device Finapress Nova, and we collaborate with the medical faculty here in Brno. So the result, what is the result? If we have the personalized input, it means all of these are or go to the unit, then the result, mean absolute error, is 8.28 millimeters of mercury. So it's let's say informative value of blood pressure, but we try to work on the improvement of these values and on the accuracy. And here are the results for systolic and diastolic blood pressure, which are about 8 and 6. So here is something about the database. We have now about 150 subjects, and each measurement takes about 22 minutes. We try to measure in different conditions, so the person does some activities to enhance the variability of the blood pressure and all the conditions. So it's quite important to for the development of the algorithm. And here we measure some more things which can be then used for various health features assessment as well, using the smartphone or the bracelet. And here are the arrhythmias detection. That's another case. We need to collect or record our own database because there is not any useful for this, because it is quite difficult to measure the arrhythmias using PPG. It's not much done, so we collaborate with hospital here in Brno, and all of these arrhythmias are based. So it is quite unique database, and we try to find which arrhythmias or which pathologies of heart can be assessed from the PPG, which is somehow known but not very properly. So it is one of our work, and the second one is to detect these pathologies. So here we can see that the signal, the PPG signal, should look like this. And in case of arrhythmias, these are highlighted by the rectangle. So we can see that the curve looks a little bit different, and we can see also in ECG, which is the reference. So here is the cardiac arrhythmia detection. This is only classification to 3 groups. It is sinus rhythm, atrial fibrillation, which is the most common pathology, heart pathology, which can be assessed using PPG and also ECG. And we will see that all the applications which are certified detect only this arrhythmia. And the last group is other, where belong all of these pathologies. And the accuracy is about 0.88 or 0.87 on independent data set. So it's, let's say, on the good way, but we need to detect the pathologies or classify the pathologies in more classes, more specifically. One of the last features which can be detected is glycemia, the blood sugar level, and it can be also done using PPG. It's quite now the holy grail in the area of PPG use and analysis. And we did some experiments with this. We extracted the features which are based on morphology and heart rate variability, and then use classification methods for this. So it's not, I think it's not possible to do it in some standard way. Here's necessary to use some AI and advanced methods. And here's classification just two groups, whether the person has higher blood pressure or normal, and the accuracy is about 74%. And if we try also the regression, it means estimate the exact number, exact glycemia, then the error on the data from smartphone was about 1.37 millimoles per liter. So it's quite promising result, but it needs some testing and development. And here are the applications, and it's almost the end of my presentation. These are CE or FDA cleared applications which are certified as a medical device. So there exist some of them. It is possible to use smartphone really seriously, let's say. And here are 3 of them which work with PPG. This Preventicus heartbeat, Epitech, and FibriCheck. This is some screen of Preventicus heartbeat app. Here we can see the beats and the classification. If it is black, it means it is normal beat. It's not any arrhythmia. And using or these blue rectangles marks the part which has low signal quality. So it is also used in this Profi application, signal quality assessment. And here is another application which uses gyrocardiography. And it means gyroscope and accelerometer to detect also the atrial fibrillation. This is the only pathology which can be detected and for which exist certified applications. And it is maybe less comfortable because the person has to lie and be calm to measure proper signals. And the last slide is about future. I don't know whether the future will be like this, but we can discuss it maybe. I think the future will be influenced by hardware development and miniaturization. So it's quite important to have good sensors, but maybe we are limited by technology because we cannot go further, or maybe we can, I don't know, maybe you will tell me. We can focus or should focus on meaningfulness and accuracy of smartphone applications because we can find many of these applications, but sometimes it is the generator of random numbers, and it is like that because you put your finger on the screen and it gives you your blood pressure. It is not possible. So it is necessary to think about these applications and the numbers which you can see in them. It may replace standard medical devices. I don't think so. It will be, let's say, some supplement to standard medical devices, some extension of them, and probably in the area of prevention. And I think it will help to have some prescription plans. If these will be implemented. It is, for example, in Germany that then the doctor can prescribe the patient the application. And there are quite many of these applications. So it's quite a good way, but I think we need to somehow be connected with the doctors and they should believe that it works. So it's very important. Yeah, and maybe the combination of sensors will be good as well to see also maybe the movement of the person, not just the health and the state of the heart of the person, but also what the person did during the measurement. And I think AI will be in this future definitely, and we will see how it will be live. So thank you for your attention. And maybe if you have any questions.
Okay, thank you for your presentation. Thank you very much. We have questions.
How many curious about the blood glucose estimation? Is the approach able to see sudden changes in blood glucose, like for example during glucose tolerance test? If you give patient like 70 grams of glucose, it will rise as blood glucose instantly, and it will drop down again within 2 hours. Could you see something like that?
We do not have such data, so we didn't try this, but I think it is possible because we can calculate the blood glucose for each bead, let's say, because we extract some features from each PPG bead. So I think it is possible. It may be possible. We have to try it, of course, but regarding the technology, I think it may be possible.
Okay, sounds great, and I definitely suggest to go ahead because it will be very interesting for medical doctors.
Thank you.
Because it's the best way how to say if a patient has diabetes or not.
It will be fine for I think, again, for the prevention area, because many people do not know that they have some
Exactly.
diabetes or pre-diabetes. So it will be quite useful tool if it works properly. And I think very much work needs to be done in this area.
Yes, indeed. Thanks for answering.
Thank you.
It seems there's some kind of task goal. Any other questions? Oh, okay, so thank you once again. It's quite interesting picture, and we will proceed with next one. Okay, so next lecture from, let's say, academia side is going to Professor Ondřej Zika from a lot of universities. You can see, so Mendel University. He's also partially collaborate with colleagues of mine from our department. So please be welcome. The floor is yours.
Thank you for your introduction. I'm coming from Department of Chemistry and Biochemistry from Mendel University, and we are also collaborating with your department. So you will see in this lecture. How many of you are working in the wet lab? How many? 1, 2, 3. Okay, so some pipettings of some solutions. I'm from area of analytical chemistry, maybe let's say bioanalytical chemistry. So this lecture will be dedicated to some development of point of need laboratory techniques, and maybe I will show you some directions or areas you can await some novel approaches and novel types of determinations. There is short synopsis. I have 8 stories which could be told to you today. So we will start from the scratch. Why we need to develop point of care or point of need methods in bioanalysis. Let's say there is big motivation to replace the big machines, golden standard analytical instrumentations by something what is very simple. What you can connect to mobile phone, as you saw in the previous presentation. But in the area of bioanalytics, if you are determining some components in blood sera, or plasma, or different type of bodily fluids, it's a big complication because you have thousands and thousands substances. You have big influence of biological matrix, and this makes things more complicated. So this is not such easy. In the same time, we can speak about transfer from golden standard methods to point of need. And what does it mean? What is the difference between golden standard methods and maybe, let's say, real world use methods? If we look on the point of care and point of need, what is the difference? Point of care, you can place in the hospital care, definitely yes. In the bedside, definitely yes. Usually it's operated by somebody which has some skill. That means, yes, could be nurse, for example. If we are talking about point of need methods, that's a little bit different. We can use it anywhere and it should be operated by anybody with no skills. Yes, this is, from my point of view, this is the biggest difference between these two abbreviations. That means if we are going to point of need, the ease of use needs to be bigger and bigger. And also the technical complexity needs to be lower and lower. Yes. And if we are going to golden standard analytical techniques, the technical complexity is higher. For example, mass spectrometry, HPLC, and etc. But in the same time, we need to have IVDR and in US FDA approvals for these techniques. Without this, you cannot use it on the market. You cannot use it. And this is the biggest pressure on the developers in the startups. These two abbreviations, these two certifications. In the publications, in the Web of Science, you can see many point of care or point of need prototypes. You can see paper fluidics, various arrays, beads, magnetic beads, different types of beads, microfluidics, and we can have target proteins, RNAs, exosomes, DNAs, many. We can have very big set of data for some statistics. And that is also a little bit problematic because each method provides you different data with different errors. Let's speak also about some context, sustainability. You remember what happened in Japan. More older people, more older people. We have the same problem here in the Czech Republic. 8.5 GDP we are spending for medical care in Czechia currently. This is data from 2022. It's higher this year. This is mostly for people going to retirement, to older people. It's logical. And in the next 20 years, this number will be higher. So it brings bigger costs. And also we are thinking about the healthcare standards. These should be also higher. So, sorry. Simultaneously, there is another threat. We need to put more money in defense nowadays and next years. And this is another big pressure. So there are two big pressures on the state budgets currently. That means our motivation, prevention based on the early diagnostics is much less expensive than subsequent care. We need to be able to put novel technologies like was presented in previous lecture. It's the same motivation to increase the spend for the money for healthcare in the pathological state, let's say. That means once POC and PON methods meet these standards, we can use it to increase of early disease monitoring, personalized monitoring of patients when they are under the cure, or monitoring of rare disease where you cannot spend some investment or money because this is rare methods, rare diseases. This is not very interesting for producers of the test. So you need to cover it by low-cost method. And big future role is also in the longevity segment. I will start with first technology we are using for development of novel methods. Magnetic-based bioanalysis. Here in this publication, which now have hundreds of citations, you can see how we can modify magnetic particle. We can connect antibody, peptide, nucleic acid, and different other ligands to be able to catch our analytes, our molecules of interest from bodily fluid, from diluted blood, from sera, from plasma, and other. This is the common protocol, how it works in the laboratory when you are pipetting solutions. You have some appendor with your molecules of interest. You will add magnetic particles. These will catch your analyte. Then you will guide it by magnet on one side, and then you can do the elution. You can do it twice, maybe 4 times, 5 times, and you are getting more clear and more clear sample. And you are also doing a pre-concentration. It's very simple way. I will make small exclusion in the history because these types of thinking we had from 2009. This was some first schema of some assay for detection of 8-hydroxydeoxyguanosine, which is marker of oxidative stress on the nucleic acid, on the DNA. We had this automatic pipetting station, and we designed some protocol with magnetic particles covered with antibody to do some analysis, and our, let's say, readout was done by electrochemistry, by this flow-through cell, which is normally used by HPLC. And this is the protocol. We have magnetic particle antibody. We are catching our analyte, which is here. And then we have 2 other antibodies. And in the end, we have enzyme alkalic phosphatase, which is converting our substrate, which is naphthyl phosphate, to naphthol. This is electrochemical active. We have electrochemical readout. We tested it on the urine samples. That means we had some groups with different descriptions. This was our first method employed. Here we can see our first, let's say, microfluidic setup. We used electrochemical cell for readout, and we were taking our sample from this plate. It was around 20-30 microliters of the substrate on the cell, and here is the simple schema. It was not covering whole protocol, definitely not, but it was our first microfluidic device, let's say. Because we are using magnetic particles, we need to be able to produce them. We are using 3 types of production of magnetic particles. One is microwave steel autoclave. This device is also used for, let's say, synthesis of peptides and the protection of peptides from some sorbent. Second way is to use steel autoclave in some volume. You can see that there is difference in the yields of the material of your magnetic particles. And also we can use big batch production line, which we design. And this we can use only in the way of precipitation method, which is not using pressure conditions. We are able to produce from 1 to 10 grams of material, which is very big batch. These are the products we achieved. These 2 are from the precipitation methods. This is from the microwave synthesis. There is a difference in the shape. Also, we can do some modifications of polystyrene cores by the nanomag, and also we are able to decorate it, for example, by golden nanoparticles. So this is some scale of products we can achieve in the laboratory conditions. Very important point is characterization of these products. Main characterization methods: electron microscopy. You can see picture here, and This is scanning electron microscopy and transmission electron microscopy, when you can see also the layers on the iron oxide core. Then also you can use transmission electron microscopy with EDX for checking which atoms do you have on the surface of your particle. Then you should also use dynamic and electrophoretic light scattering detection, which can tell you more about your size distribution in your batch, and also the beta potential in different pH. But there is important point: your product needs to be in dispersion, 100 dispersion. Once it will be sedimentating, that's problematic. This is not applicable for all types of particles. Then also you need to use X-ray photoelectron spectroscopy, XPS, for another characterization, and also FTIR for checking of the surface functional groups, which is very important because you need to have some groups to be able to functionalize, for example, by antibody or different type of ligands. Also, what is important is magnetometry, because from batch to batch, you can get different material, which has different, let's say, quality in the magnetic area. There needs to be the same, how to say, same strands of the magnetic field in your material. Here is the last method, which is the low cost. We are using that for checking of rate of sedimentation of our produced nanoparticles, and this is based on the turbidimetry. Okay, only last slide for this. What is also important, we check the oxidation durability of our material. That means after, for example, 1 year, these materials should have the same properties. Also, the checking based on the higher temperature should also make this testing time shorter. Okay, we have another part, immunodiagnostics for point of view bioanalysis using magnetic particles. So we cooked some particles, characterized it, we did some conjugations, and then we can have something like this. This is chemiluminescence immunoanalysis, which is magnetic assisted. We are calling that magnetic assisted CLIA. That means abbreviation of MALIA, which is name of our prototype device, which are developed under the Nantel startup. The principle of CLIA with magnetic particles is here. We have magnetic particles, one antibody, we are catching one analyte. It could be anything what is immunoreactive, hormone, protein, different substances which has some immunoreactivity. And on this antibody, we have acridinium. This is not enzyme. This is organic molecule which is stable, and we can use it for making the light. We are adding some solutions to make it blinking. This is the signal of this light. This is, let's say, batch of the photons. Doesn't matter in which wavelength it is. We are catching all photons. It takes hundreds of milliseconds, so we need to be very fast to catch it and to integrate it. And then we can provide some quantitative data. This is the team which developed the first prototype. These two guys are from Faculty of Electrotechnics. So you have talent here. This is my brother and this is my old colleague from the diploma student studies. So we have machine, and how we can make the analysis. Okay, we are taking blood. We can take only 10, 20 microliters. If we will dilute it, it will be working. But sometimes better is to have plasma. For that, we need to take 50 to 60 microliters of blood. Then we can proceed some 20 microliters of sera, or we can use direct plasma. It depends from biomarker to biomarker. We are talking about capsule copulation concept. If we want to use this technology like point of need, this must be based on very simply way. That means you will put this cartridge in the machine, you will put sample in the second hole, and then it will bring you the result, some number. In the philosophy of telemedicine, you cannot see the number. This number could be sent to your medicine. He will check it because he knows your context. He knows what is your weight, what is your blood pressure, what context information. This is very, very important in the ethical way. Then he can tell you, okay, go to the hospital, go to the specialist, which type of specialist, and etc. This test is only for one biomarker currently, but we are developing tests for 3 biomarkers in different area. That means the way of use is same like you are cooking espresso in an espresso. Maybe you know it. You will buy different capsules according your intention. What do you want to know about your health? Very important point. When we are developing anything, there needs to be correlation with some big alternative in the hospital. Now, CLIA is used in, for example, this machine. This is high throughput CLIA device, which is replacing old method, which is called ELISA. And it will be replacing more and more because these machines are working on the random access analysis, let's say, principle. You will put one sample, you will get result in 20 minutes. Okay. Our device is much smaller, could be mobile, could be everywhere, could be operated in the point of need way. Okay, it is doing one result between 12 to 15 minutes. It depends which protocol we are doing, which biomarker determined. But correlation is the essential. This correlation is made on the adiponectin biomarker, which is pre-diabetes biomarker. And it is made on the blood sera from the real patients. So we have some use cases for our Malia device. We can use it in 2 applications we are thinking about now. First application is in human diagnostics in the neonatals, which are after surgeries. From the ethical reason, you can take only small amount of blood from them. So we have collaboration with the child hospitals in Brno, and they are interested about these markers, high sensitive CRP and procalcitonin, to see what is the prognosis of the neonatal. And we are prepared to analyze only 20 microliters of blood, and we can do it, for example, 3 times per day, and this device will be on the bedside. So this is one use case. Second use case is going to the segment of life science, because you know that drugs are tested on the mice, on small rodents, and there you can take the blood from these small animals by terminal taking of the blood, or you can take only a couple of microliters. And that is the position for using in the Malia. And there is some chance to replace ELISA and to provide some detection alternative. And it could be used in the rodent facility, just on the place, just on the side. So this is another use case we are thinking about, and we are in connection with facilities. Electrochemistry for point of need bioanalysis. our past work is, for example, this is one use case we developed. More or less, electrochemistry in point of need is more or less based on the screen printed electrodes, which you can produce in high scale and can put on these electrodes on the active surface different nanoconstructs, and you can also make some modifications, like in the case of magnetic nanoparticles. This case, it was dedicated to determination of HTP toxin, which is hazardous contaminant in the crop area, and we did some constructive first antibody which catch that HTP toxin, then another antibody which is connected to enzyme alkali phosphatase, and there is analogy with the approach I described previously. So we are detecting naphthol as the product of the enzymatic reaction. There is also one specialty. We used electrochemically reduced graphene oxide for increasing the sensitivity of this sensor or biosensor. This is very convenient way to connect magnetic particles with screen printed electrodes, because magnetic particles brings you preconcentration and increasing of selectivity. Screen printed electrode bring you the capability to make some detection, to make some readout in very low cost. So this is nice philosophy to connect it. Okay, this is not such easy, because there are many steps what you need to do, and we will go to the problems in the development in this area. Before that, I want to tell you that we are solving this project, which is, let's say, in the basic way, for environmental use case. We are trying to develop screen printed electrodes and magnetic nanoparticles, which will be modified by special copolymers, and we are trying selectively catch these contaminants of environment, paracetamol, neonicotinoids, and other, and then we will have readout by electrochemistry. So we are developing something in that area, and we can continue with SPEs. We can ask if we have real-world applications around us based on the SPEs, the screen printed electrodes. We can buy many types of bare screen printed electrodes from different producers, but the problem sometimes is repeatability, reproducibility, also sometimes transport durability or environmental stability. That means there will be change in the humidity, and your electrodes is somehow moving. It's not the same like previous batch. Many problems. So why this is not successful now? Maybe because of this. So we are trying to develop the solution, and therefore we aim to design and build fully automatic benchtop device, which we can use to test hundreds or thousands of screen printed electrodes, and also which we can use to develop the sensors and biosensors by automatic way. So this is some first prototype, and there is our solution. Fully automatic benchtop electrochemical station. We published it here. So you can see it here. We have rack for electrodes. You can put there 192 electrodes. And also we have 4 positions, dipping positions. It has about 3 milliliters. You can use it for example, calibrations, testing, modification of these electrodes, and other. We also have to develop our own software. So we have cyclical tomograms from one of the case. And also we have developed rack for the electrodes to prevent the active side of the electrode against the scratching. This is also the big problem if you will get some electrodes from some commercial producer. To preventing of scratching of active side is important. So I will go back to IVD and IVDR regulations. These regulations tell you that you have to have some coefficient of variance in your bioanalytical approach. For example, for PCR, it is around 5%. For immunodiagnostics, it should be below 10%. For example, for lateral test, COVID test, it's around 15%. I think to 20. It's worse. Yes. So we can speak about skin printed electrodes. We tested these electrodes. These are commercial ones. These are from the production from one of our partner from laboratory. These are not CVs, these are standard deviation. It's different. But after that, you will count it. You can see maybe this can have potential to be within this CV. It's not. And this is bare electrode. Once you will make some connections of some nanoconstruct and you will have some interactions, your error will be higher and higher. So you need to have the space to absorb your error if you are developing some biosampling system based on the screen printed electrodes. We did some validation of our benchtop electrochemical station. We used very basic for example, yes, this is, let's say, basic sensor for paracetamol and dopamine. This case is for paracetamols. We used this type of electrode. We decorated the surface by golden nanoparticles, and this whole process was done by benchtop electrochemical station. And in the next table, there was skilled operator which did the same by his hand. You can see the difference between repeatability of this process. And he was really skilled operator. Maybe 6 years he did only this development. So this is how it works. Okay, there is another one. This is the development of molecularly implanted sensor for polyphenol detection. This is very basic schema. We are taking the screen printed electrode. We are making the electrode deposition with hitosan, then enzyme which is called lacase, and then we are doing the enzymatic reaction and converting our substrate to product. We are making detection of polyphenols. This is very basic. Just right now we are under the master thesis production, so this is only to show you very shortly. Another part is dedicated to in vitro chips, and this is honestly area of colleagues from Faculty of Electrotechnics. So I will go smoothly through, and maybe you can ask them if you will go to the laboratories tomorrow. Then you can ask, for example, Ludovico Migliaccio will be the most
On Thursday.
Sorry. So here is the example of the use of such chip for cardiomyocyte characterization, and have some stimulation and then recording of the electrochemical signal using this EIEIN chip. Another application is on the transparent microelectrode array for in vitro experiments for different types of cells. Here is the one novel thing. They are using ITO glasses, but if this is connected to thin nitride, it has better how to say results, and it's more durable for this process. We are going through the chips. So microfluidics for liquid handling in bioanalysis is very important skill. We want to use this skill in cooperation with the Department of Microelectronics for the future development of novel techniques, because we think that this is the future of the diagnostics, especially in point of need area. So here we have some common design of microfluidic chip. In next slides, we will go through, and there will be one case based on this design. But basically, you can use polymethyl methacrylate, CNC machining, PDMS, microfabrications, crystallography, and different approaches to have some prototypes of chips. You can see in fabrication, here are summarized, but what is the, let's say we are starting with that currently, most convenient is 3D resin printer, which can be very fast. You can produce in large scale your chips. It's enabling also to do embedded channels, and you can use biocompatible resins for some use cases where you want, for example, cultivate the cells in the chips. We had one experiment which just started on this, and yeah, there is limitation in the resolution, but for first test, and especially if you are not using some solid liquids or only liquids, and you don't have some particles inside, you can use it. On the other side, this is a type of preparation which is the most finished. This is based on the silicon wafers. There is very high resolution of the product, and we can see examples. This is Tesla mixer, which is used for mixing of different components, liquid components for the analysis. One separation chip, and also there is some proposal for the for, let's say, cutting of the red blood cells, because sometimes in your technology you don't need to make the lysis of the cells by chemical nature or thermical, or let's say by cold. It's sometimes better to use physical cutting of the cells, and we are trying to use this design in one of our experiment. Maybe Ludovico, if you will go to the labs, he will show you, because we started to optimize that. This is the last part, and this is dedicated to molecular diagnostics, where we are using magnetic particles and also microfluidics. So this is the reason why I put it in the last part. Maybe from the COVID times, you all know what is the PCR, what is the lateral flow test, COVID test, and everything. From that times, also big popularity was put on the lamp-mediated isothermal amplification. This method in that times was very simple, and everybody will use it. Okay, this is not such easy. Yes, if you have something in the clear conditions, if you have standard solutions, it will work. But once you will have complicated sample, once you will have some matrix, it will be complicated, because this method then is not reproducible. If we will compare LAMP to PCR, PCR takes 1.5 hours. You will use 2 primers. You are making cycling of temperature, and you will need this big box. You are doing fluorescence readout. If you will use our first prototype for LAMP, you are using this method only in one temperature. The method is shorter, and yes, okay, you are using more primers to be sure to have the specificity. If we will do it in laboratory, we can also have fluorescence readout or colorimetric readout, or you can also use electrochemical readout. But what is the problematic point? You need to have your sample, how to say, in same solution, in same conditions, same salinity, same pH, same concentration of your another contaminating substances and etc. Therefore, we try to use magnetic particles to catch our target nucleic acid from the sample. We develop different types of magnetic particles. One type can bind more genomic DNA, another type can bind RNA, so we can use it for both types of viruses, for example, and we tested these particles, and we validated on our land assay, which our prototype. We checked that fluorescence and colorimetric sensitivity is pretty the same. We checked that there is no inhibition effect of our magnetic particles to the BST polymerase, which is enzyme which is working in land. And we are under the development of another types of assay based on this technology. So the last part of the presentation, let's say this is the last slide, is integration of this lab assay in the microfluidic chips. Let's say this is the schema which you saw in the presentation. You can do some cell lysis, binding on the magnetic particle, RNA binding on the magnetic particle, washing of this particle, and then you can do some basic tests. This is the prototype of the microfluidic chip, which is used in this prototype device, which can make heating and also recording of fluorescence. And we can do one thing: we can put our magnetic particle with the yield of RNA in the chip, and then we can move by the magnet to a chamber where we will add the master mix, and there we can run the reaction, the lamp reaction. This is the common schema of the chip. We are trying to develop something which is similar to this. So this is under development. I can show you all this schema for that time. So we can say this is the BioChip, probably. Okay. Maybe it has this definition. And there is, for the end, call to action for you. Any of these presented technologies are available to, for example, for some project cooperation or any other cooperation. We are trying to make better point of view diagnostics for healthcare, veterinary care, environmental safety, and also for food tech safety, because we believe that our technology could be robust enough to be able to detect different fluidic samples. But you need to choose if this will be immunodiagnostic or molecular diagnostic. So you can contact me on that email. And also for the last thing, these are the projects which are supporting us. And this is my research group for biomarkers, and also guys from the Faculty of Electrotechnics. If you will be asking about chips, you can ask this guy, Ludovico. So thank you very much. If you will go to Brno by plane, you will see something like this. Brno, in the runway. In the night, of course. Thank you.
Thank you very much for the presentation. Are there any questions? Since I know Czech's work well, so I don't know what to ask, but I think we will have some time in the networking and discussion later on. Before we start with the last but not least presentation, which will be given by Mr. Kamra from IQS Nano, which is the company we are going to visit tomorrow morning. Once again, those who not respond whether they will join us or not for tomorrow's excursion, please give your decision to our secretary. As far as I know, we have now about 12 people who would like to join. So We will leave approximately 9:30 tomorrow morning from our faculty, Technická 10 Street. The bus will be ready in front of the building. So please just try to manage your time and arrival there. We have some time. So if you don't mind, let's make 5 minutes for a short break, and then we will finish with the last presentation if you find. Thank you once again. So we will start, let's say, after 6-7 minutes. To keep the schedule.
It's microwave and metal block. This is the best because you have nice homogeneity. You are doing the precipitation method. It's a little bit worse. Sometimes you need to do some. Yes, it's a precipitation. It's much better for getting a high scale than if you do some fractionation. Sometimes you can do the fractionation so by or say you for some fractionation. You eliminate the particles. But they can take the foundation.
This component microwave extended its
There's a spin in the crystals. Microwave is the definition of one microwave. There's fans like nanometers. It depends on the so yes, you can Thank you very much. Yes, we have started to use it and test it. This is not the because it has another use. This check. The form is I guess it seems like cases
Okay, just a short break is over, and let's start with let's say industrial section.
Only one.
Industrial section. So it's my pleasure to introduce Dr. Mario Kandra, who is working for the IQS Nano company. And like I mentioned, the company we are going to visit tomorrow. We will have the opportunity to see their labs and what they are doing there. And I think this is just some kind of introduction to the stuff what the IQS Nano is doing. So please, floor is yours.
Yeah, thank you very much. Yeah, I'm Mario Kandra. In the company, I am biomedical engineer, so I'm more focused on developing two-photon lithography for biotech and biomedical application. But first, I would like to talk more about two-photon lithography. If you know what the technology is or you don't know, I will explain. And I would like to thank the presenter before me because he basically showed our motivation, what we are doing and why we are doing. Because as you saw before, if you paid attention, there is like in a way of 3D printing, everybody knows 3D printing. And right now, everybody wants, or everybody has 3D printer. If you have SLR printer or fused deposit printer, it's great. It's rapid. It's quick, but in a way of resolution, it has some limitation. On the other side, there is a lithography technology, which is great in the resolution, but there is a limitation in a rapid prototyping and manual handling and everything that. And there is small gap between that, and for that we have two-photon lithography. Because with this technology, you have basically resolution of lithography, and still you have basically 3D freedom of creating things and rapid prototyping. And you can go from micro, which you start with a resolution of hundreds of nanometers, and go to meso, where you can print 1 millimeter on or structures which are like larger. The idea or how the two photon absorption works is that my boss tell me that I should explain it on the way of flashlight, because one photon absorption, as you can see here, if you have fog and you shine with the flashlight, you just see one straight line, because there is some energy and you can go. But in the way of two photon absorption, you have two flashlights with lower energy, and when these two flashlights meet, then the like point. There is a like 1 pixel, like volumetric 1 pixel, which is like we call it voxel, and there when everything happened. So in that way, you are not you are in like 3D space, and you can like basically move with this 1 point everywhere. So this is basically idea of 3D printing, and this is nice of the 3D printing. In our company, we are using green light femtosecond laser. Why we are doing this? Because it's better in a way of resolution, and we can reach like smaller and smaller and better resolution. And here what you can see here is that this voxel is like basically 3D area where the whole photo like the chemical reaction happened, where the photoinjectors are activated, and from basically liquid phase you create one solid voxel. Okay, so for what we are using for the like basically moving the laser in the area is acousto-optic deflectors. Normally are using mirrors, galvanomirrors, which are like moving with the laser on to X and Y like axis, but they are mechanical and they have like limitation in speed. We are using these acousto-optic deflectors, and we are moving with the laser not mechanically, but with a wave in a crystal. And what you can see here is what you can see in a basically objective is that this is an area where we can like print, and then we can like move with the laser and create different patterns. If you go like with a larger area, it means that you want to print like, I don't know, centimeter to centimeter area. We are using nano sweeping technology. You can imagine it as a basically dynamic brush, the really smart brush. When you go from one side to another in X on Y axis, and there you need also not just objective, but you need stage. You need a moving stage, and this stage is moving, and with a laser, which is basically one line of voxel, you're going on this area and you print. What is great about this brush is that it's basically created from these one voxels next to each other. So you can basically you can on and off these voxels. You can you can basically choose if this voxel will be used or not used. So you can change in a basically moving of the stage. You can change this line of brushing and then print specifically what you want. In a way of resolution, as I said, you can go from really high resolution and from like 100 microns to 150 microns. And basically, when you change the objectives and you changing the magnification of the objectives, you can go to really big structures. Big, I mean, like in a way of one voxel, it goes like 10 microns, maybe more. It depends on the objective. And then you can print like larger structures, but you have to be sure, or you should know that, yeah, you have larger structure, but the lower resolution of printing. So
the advantages of this technology is resolution. You can print with a height aspect ratio. It means that the height of the structures to compare it with the base it can be 1 to 10. And of course, you can basically mix and match this printing technology. So you can print the microfluidic channel by laser ablation, by different 3D printing, and can you go to the basically our printer and we can print something functional in it. Then, of course, you can print complex 3D objects, and of course, different shapes and angles to that. And of course, that we can smooth surface with a great resolution also can be printed. Also, we developed our own resin. It depends what you want. It depends on the application. So if you going for more like optics, you want to like building chips like from more optic area or something like that, we have resin for that, optopure, optobase. Then we of course will have bioresin, and of course for more like prototyping thing or mechanical or microfabrication things, we have basic and hybrid resin. So just to conclude this, what we offer, what we have like really fast printing machine with high precision and resolution. Of course, there is a flexible 3D microfabrication, and of course, what we offer is that not just we give you the printer, we give you like device, we give you printing material, we give you like ideas, know how to print, how to adapt printing for what you need, and of course, we can customize the printer for basically what you need or what is your focus. So how it works, if you're doing 3D printing, it's basically same. It will be easier to you to understand how the workflow flows, but we want to like do more advanced. So this is not just you have a 3D model and then you put 3D model into our machine. Yeah, of course it works, but what we offer more is that you can just add the bitmaps and then you can print by the bitmaps. Then you can go strictly if you are, or if you low programming, if you're low programming in the C++, then you call and you can create the code, and code will basically run the machine. And then of course we have like simple object library if you want to print something basically not that complex, also working. Then what you need is substrate on what you will print. Yeah, it can be silicon wafers, can be glasses, can be different materials from the different like 3D printer like resin. And of course our resin put into machine, then magic happens, and now you will have 3D printing part. And of course, most of the time you need electron microscopy to see what you print. So basically, when you print something and when you go to electron microscopy, you will basically pray that something is there and hope that there is not something, that you print actually something. So the printing process in a machine goes like this, that you will print in the x-axis and then you're moving with the z-axis and then you print the whole object and structures. So here you can see what you actually can see, and it's just like moving objectives and shining of laser. So, and what we are our focus on, what we are cooperating right now in areas of biomedical and tissue engineering, surface functionalism, metamaterial, integrated microfluidics printing, flat and 3D optics, electronics, and of course microengineering. And here, as you can see, like just the examples what we can print in a way of like bioapplication, microparts, optics, maybe just microengineering and some specific microparts, of course, microfluidics and 3D scaffold. First use case, what I would like to show you is the basically fiber face printing. When you have fiber, we are able to basically print strictly to the fiber, so we can find and align our printing with the fiber, and it's great in a way of optics. And if you want to do something like more focusing of the like light, or you want to like bend the light, we can print the specific functional parts on it. Then of course we can print on chip if you have specific optical or mechanical elements on these electronic or semiconductor components. Then what I'd like to show you is like some use case. What we did is that guys from the Faculty of Mechanical Engineering, they have like they're using scanning near field optical microscopy, and they have fiber, and they want like microprobes on the fiber, and we printed the specific design, which was like it takes like half of the year to develop all of this. Firstly was like just this, and then we add parts because it's not that easy, as you can see in the video too. We make sure that if you have the fiber, you should like know exactly what we are doing and when you are here, and to basically put the fiber on the microprobes, and then at the end they use it for scanning microscopy. So we know what the idea was great, but at the end we printed not just functional parts, but also supports, also like basic navigating parts for fibers. So it was not just printing, but also a lot of the engineering to create the functional thing. Then the second use case I would like to show is that electron emitters, where we print basically the base, the specific structures, and then the structures was functionalized with the coating, and then used in the research. If I go like for my biomedical area, firstly, what we did, we need to have the material which is biocompatible, and together with Department of Biomedical Engineering, with Ina Zamberg, we basically create they tested for us with biocompatibility, so we were sure that we had non-toxic material. One of the in case, well, yeah, we have biocompatible, but then we want to have like low autofluorescence, because you have cells, you can print something, you have with cells, but when you start to doing microscopy, you figure it out that everything is shining. Cells are shining, the material have autofluorescence, and then you don't know what's going on. But in that case, we create this low autofluorescent resin. Of course, it should be sterilizable. Yeah, and so you can sterilize with UV autoclaving, of course, ethanol sterilization, and of course thermal stability in the case of sterilization, or if you want to work with the cells at 200 degrees, it's up to you. We can do that for you. And next, we try to, or we have some cases where we want to show is that we can print nozzles or like microneedles, but not just microneedles. These microneedles can be like hollow. They can be used on the chips, on the more advanced chip, but you can use it as electrodes, or you want to like deliver drug into body, so use it to penetration of the body, and can be part of the more advanced chip. And not just creating the microfluidics of things, we also are providing the mastering. It means that we can create master, and then from this master, you can basically fabricate more patches, which they have, and these patches will have these microneedles, and then you can go with like high throughput fabrication and use it based what you want to, or based on your research. And second thing, or third thing, is like stands. When we can provide like stands which are like in the way of height is height, is like they're really high, but in a way of resolution we still have the lowest resolution as possible to create the stents to have like functional thing, which can support with basically structural support and diverse medical application. And then, which is like for us at the beginning, the most crucial part is to show that we have biocompatible material, but we can print it and we can see the cells on that. So in that case, we cooperate with the Department of Histology and Embryology, and they provide for us the cells, and we print the material. For this specific cells are embryonic stem cells, and for that we need to code the structures with a specific coating to basically for them to be happy and to adhere on the scaffold. And then what we show is that we create scaffold. We basically provide scaffold, and cells adhere and proliferate and create 3D structures. The next thing is microfluidic. Of course, we are here at Advanced Chip Design, so we also can create microfluidic chip for you, but of course in a way of size which are still lower than some SLR resin 3D printing. So here you can see the microfluidic which basically print or print by it's fabricated by laser ablation on the microscopic glass, and then you can see the same microfluidic chip creating by our machine. By our machine, which the resolution of this chip is smaller and can be used for like with a less volume of media on more specific research. Then what we are able to do is to not just create the microfluidic chip, but to induce the functional part into microfluidic chip. And it means if you have two channels and you want to separate them, we can create the separator, and which is basically filter, and it can be adapted if you want the cells go through, if you don't want to cells go through, and you can create more advanced microfluidic chip. And of course, what we can is to print scaffolds inside the chip. So if you want to test some cells on scaffold and you want to do it in microfluidic way, we can create the microfluidic chip and we can print the scaffold inside that. And the last part, what is great about this 3D printing is that in a organ chip research, there is a lot of publication where the scientists use the membrane for basically separating two channels and create some barriers. But what we can do the same. We can also print the membrane. We can also create the barrier. But what we can add, we can add the 3D to this barrier. So we can on the both sides of this membrane we can print the 3D structures, and we are able to put it into the chip. And this is great. This is what is great about this technology. So right now we are providing the academic or industrial R&D printer, where we are mostly focused on prototyping, on microfabrication with a small batch print. Of course, you can buy our machine if you want, and of course we are providing just printing. If you want to try something or you have any idea, talk with us and we can talk if we are able to meet your specification. And nextly we would like to do like the better machine with which will be faster and will be more focused on industry and high throughput fabrication and of course automatization. And so if you have any ideas you want to talk of, you have to, and you don't know if you are able to fabricate, definitely talk to us, and we maybe maybe we'll be able to print it. And thank you for your attention.
Thank you for your insights to IQS Nano. So it's a very nice invitation for tomorrow's visit in extrusion. Are there any questions? Microfluidics.
I have a quick questions, actually two.
Yeah.
The first one is because you say your instrument can be used to print different kind of materials, and I saw in your slide, you will use the laser to assist your 3D printing fabrication. So could you in your system, could we could we change the laser power if today the material if that is metal or harder, tougher material?
Yeah,
So
definitely.
you can
Yeah.
change the laser power.
Yeah. Specific every like resin needs like specific power of laser because there is a photo initiator and they are really sensible. So yeah, the type of the specific type of material needs specific power of laser. Yes.
And the second question is from your presentation, most of the products, the fabricated products seems like a bottom-up process, like you print them step by step and to build up the 3D structure. So could you do the top-down like etching process to make the 3D structure?
Yeah, it's a good question. So what we are using is hopefully I will say the right, but we have like positive resins. It means that you will beat and then you basically wash out what you are not used. But of course, theoretically, yeah, we can do that you will have the negative resin, so you will like basically print down, or you will take out the resin what you don't want, if I understand correctly your question. So yes.
Thank you.
No problem.
Questions?
Yeah, thank you for the great introduction. Just wondering the supporting material or something like that.
Yeah.
To the structure. Possible.
Yeah, it depends how long you want to like hang out the structure. What we tried it was like 200 microns, I think, if I remember, or around 200 microns. It can be like print in a like without the support. If you want, this is what you like ask.
Oh,
Like 200 microns. I mean, like.
So you are asking about the thickness,
Or like.
supporting.
Yeah. So we right now what we know that if you have like two structures and you connect the structures in basically in air, we know that you can connect it in a distance of 200 microns without support. Yeah, it will your resin starts to bend. So it means the weight of the printed structure will like go lower because of the gravity or because of the weight. Yeah.
So basic principle of your device machine is 2-photon programming, right?
Yes.
So can you use your machine for represent the negative photons, for example, SUA?
Oh, I'm not sure. I'm not sure what you're asking. Like,
so when you do you know SUA?
you mean resin SUA?
Yes,
Yeah. Right now we try to develop our resin, but we try it, and yeah, we can print SUA, of course. But we optimize our resin, so definitely we need to optimize to get the resolution and thing. But we know that we can also print with the SU8.
Your question?
What's the smallest dimension you can print?
Yeah, it's like 150 nanometers. Like right now, what we know. But yeah, we find out that it depends on how much time you sitting with the machine that you can find the lowest point. But right now, what we offer or what we know that we can print is 115 nanometers.
Is it possible to ceramic?
Yeah, it's quite interesting that you are like second person in like 2 weeks which is asking on that. And right now we don't have it. We need to like really do the whole developing thing on that. And so yeah, right now we don't have the material for that. Maybe yes, but
Okay,
That's correct. Like if two polymerization increases the resolution, improves it, would free photopolymerization improve it even further?
yeah. You using femtosecond laser and 2 photon is really, how to say, is the explanation of technology, but there is not like 2 photon, just 2 photon yet. It's for femtosecond laser, so it's like shining in the. So I how to say, I think not. But yeah, I'm not the physics and optics guy, so yeah. So this maybe if you were going tomorrow, you can definitely ask.
guys,
Yeah, more
discussion.
yeah, better than me.
Okay. Plenty of questions. Any other? We still have some time to ask. Okay. Okay.
Yes, I have one more stupid question because when I visit your website, you make more feature on the human hair, right?
Yeah.
So because I'm working on lithography on one-dimensional fiber, so can you make any feature all around
Fiber.
the fiber?
Oh, that's a good question, and we definitely talk about it tomorrow. Yeah. If you want to, like that, you are the first guy who asking this. So
Yeah, because
so
I'm really interested to photolithography on the fiber, but unfortunately I don't have such a good machine.
Yeah,
So
yeah.
we use, as you know, Heidelberg in Germany, they only allow for the one case,
Yeah,
right?
yeah,
It
yeah,
is optimized for the just wafer.
Yeah.
So what I'm thinking is you are really good in 3D. So I think it is definitely applicable for
yeah.
3D software.
Yeah, it would be hard to get, if there's a fiber and there's a focus point and there is the laser, you should be somehow rotate the fiber and then the print. And yeah, definitely if you buy the machine, we can talk about it.
Good point.
But yeah. To be honest, it's a great question, great like technology question, but
He's also a businessman.
yeah, I'm trying to. Yeah, so
That is my
maybe yeah.
problem, only.
Yeah, always. It's always fun. Yeah. But tomorrow, yeah, to be honest, they just give me number and I figured out that I know the bad number. So tomorrow you can ask, but no, it goes like around 350 thousand euros.
Okay.
How about in US dollar?
Yeah.
It's a little bit more expensive because the ratio between the euro, €1 is about $1.1 or something like that.
Yeah, but of course the price is go what you want and what like accessories, because if you want just for one thing, you don't need like 3 objectives.
Yeah.
You just need one.
So it depends
so
on the tools you
yeah,
have.
it depends
Yeah.
on what you want to do. Yeah.
For more.
Yeah, but to be honest, I'm not the marketing guy and salesman, so I don't know how to negotiate the price.
So,
So.
yeah.
Maybe you will have 50% off. tomorrow.
Serious.
No.
Yeah.
Okay, so it seems that we have finished just on time almost. Thank you once again. Thank
No
you
problem.
for your plenty of questions and answers. And now let's proceed for the networking phase. So I just assume you have already started during the lunch and the breaks, but let's continue. There is also some refreshment over there. So we have at least maybe 1.5 hours to stay here, and we can talk to each other and just to exchange what we have seen. And like I mentioned, tomorrow, those who are going to visit QS Nano, maybe you can negotiate about the devices and this stuff. We are leaving 9:30 a.m. from the Technická 10 street in front of our faculty. So thanks for tomorrow attendance and enjoy the rest of the day. See you tomorrow. Thank you very much.